In this video, we will learn about measures of dispersions. Specifically, we will understand the concepts of range, mean absolute deviation, variance, and standard deviation. Let's consider an example where we analyze the scores on a test of 1,000 students from two different schools. The scores range from 0 to 100, and the histogram displays the distribution of grades from the first school. The school's score show an average score of 80 and a range of score from 60 to 100. The range is defined as the difference between the maximum and minimum score on a dataset. And in this example, it has a value of 40. In comparison, we can observe the histogram from the second school. This school also has an average score of 80. However, the scores are more concentrated, ranging from 70 to 90, and displaying a range of 20. Next, we will analyze how to quantify the dispersion of the scores around the mean beyond the range. Taking 5 students with scores of 41, 89, 67, 98, and 55, we can visualize these scores using a bar graph, with the x-axis representing each of the 5 students and the y-axis indicating their respective scores. We can begin by calculating the average obtained by summing all the scores and dividing it by the number of individuals, in this case 5. Our average, depicted by a dashed line on the chart, is a score of 7. Next, we can calculate the dispersion of the first student by subtracting the student's score from the average score. In this case, 41 minus 70 equals negative 29. We can repeat the process for the remaining students, bearing in mind that if the score is above the mean, the value is positive, and if it is below the mean, the value is negative. Let's move this data to the top to create more space. Our initial attempt might involve summing all the dispersion values and calculating the average, as demonstrated here. Unfortunately, this approach will be ineffective because the sum of positive and negative values would cancel each other out, resulting in a total of 0. Consequently, we would be unable to derive a meaningful measure of how much the values deviate from the mean. In our second approach, we would consider all values as positive and calculate the mean absolute deviation. In this method, we determine the average of the deviations using only their absolute values, essentially focusing on their positive values. In our example, we would add all the positive values and obtain a result of 18.8. We have added a dashed line to indicate the location of the mean absolute deviation. Another alternative is to start with our deviation values and square them. It is important to note that the square of a number is always positive. The variance is similar to the absolute value of the deviation, but with the added step of squaring the values. There are two versions of this equation. The one on the left is applicable when measuring the entire population. For instance, if the 5 students are the only ones who took the test, the left equation would be employed. Conversely, if the students constitute a subset of the whole population, the right equation would be used. There are several distinctions in the equations. Firstly, the symbol employed for the population is represented by the Greek letter sigma in contrast to s, which is used for the sample. It's worth mentioning that the presence of a power of 2 in the equation denotes that the values are squared. Next, there are 2 distinct symbols for the average value. The symbol mu signifies the average of the entire population, while x bar indicates the average of the sample. Although these two values are typically very close, they do not necessarily have to be identical. Finally, in the denominator, the division is conducted by uppercase N for the whole population, representing the total number of students, as opposed to n-1, where lowercase n signifies the number of samples used. The inclusion of the -1 serves as a correction factor, although the intricate details of this correction are not covered in this video. It's worth noting that if the sample size is sufficiently large, the division by n-1 becomes negligible compared to dividing by n. Let's consider that these 5 students form a sample from the entire student body. To compute the variance, we will employ the sample equation. We square the values -29, 19, -3, 28, and -15, and sum them together. It's crucial to divide the sum by n-1, where n represents the sample size, which in this case is 5. The result is 555. When we attempt to interpret these findings, we express that our sample has an average score of 70 points with a variance of 555 points squared. However, as using points squared may not be the most intuitive metric, we can introduce a new variable to provide a clearer understanding, referred to as the standard deviation. This metric is essentially the square root of the variance, aligning its units with those of the average. Assuming once more that our dataset is a sample, we can compute the square root of the variance, resulting in a value of 23.5. Consequently, we can articulate that our data exhibits a mean of 70 with a standard deviation of 23.5. Returning to our initial example, we observe that both schools have an identical mean score of 80.3. Comparing the mean absolute deviation, the first school's deviation is roughly twice that of the second school. The variance is notably more substantial in the first school. It's important to note that the units of variance are in points squared, lacking a straightforward interpretation. Consequently, the preference might lean towards standard deviation, the square root of variance. Once again, the first school's standard deviation is almost double that of the second school. To elaborate, the first school has an average score of 80.3 with a standard deviation of 9.2, contrasting with the second school's variance of 4.9. In summary, the data implies that students in the first school display greater variation in their test scores than those in the second school. Standard deviation is a widely used metric, especially when dealing with data distributions following a normal or bell-shaped curve. It allows us to interpret data within a certain standard deviation ranges, such as 68.2% of the values falling within one standard deviation from the mean, 95.4% within 2 standard deviations, and 99.7% within 3 standard deviations. This information is particularly useful for identifying outliers in a dataset when they fall outside a threshold, such as 3 standard deviations.